Hello, so today we will talk about more about modal expansion theorem, generalized or natural coordinate. So this modal expansion theorem has already been discussed in the context of free vibration. We will talk it in the context of free as well as force vibration. So this will help us to obtain a generalized solution of any multi-degree of freedom system under free vibration condition or force vibration condition. So, let me get back to what we did for a free vibration case. So, for a free vibration case using modal expansion theorem, we said that any arbitrary response of a system can actually be written as linear combination or linear superposition of the normal mode. So, we had written this as R1 into cos omega 1 t minus theta 1 plus C2 R2 into cos omega 2 t minus theta 2 and so on going to C n R n cos So, each of this actually is a normal mode. So, this is the first normal mode, this is the second normal, this is first normal mode, this is second normal mode, this is the nth normal mode, and therefore, any arbitrary response is just a combination of its normal mode. So, C1 C and theta 1, C2 theta 2 are unknowns which depends on the initial condition of the free vibration problem. So, we have even used this expression or this theorem. So, this is called modal expansion theorem, just to repeat. So, we have used this theorem or expression to solve examples of free vibration problem of a 2 degree of freedom system. Now, let us see how we can extend this to a force vibration problem. So, what happens when we have a force vibration problem? Our time response, which is C1 cos omega 1 t minus theta 1, this is the time response when there is a free vibration, but when there is a force vibration or an externally applied force is acting on the system, we no longer can say that this is going to be the time solution. So, in that case, what we are going to do in case of force vibration? We are going to write the same response as some R1 into eta 1 t. I do not know eta 1. Eta 1 t is just some function of time, and then I will write R2 into eta 2 t plus so on till the nth mode shape into eta n t. So, in case of free vibration, this eta 1 t is nothing but C1 into cos omega 1 t minus theta 1. So, similarly, for the free vibration case, this eta n t is nothing but cos into omega C n into cos into omega n t minus theta n. And for force vibration system, depending on the nature of force that we are applying, we will be able to evaluate eta 1 t, eta 2 t, eta n t. So, we will discuss further how to actually use this to solve a force vibration problem and how we can solve for eta 1, eta 2 and eta so on till eta n. So, let me put it in this way. So, what I am proposing is that for a force vibration problem, or free vibration for that matter, I can say that u1 t, u2 t, so on till un t can be written as first mode shape into eta 1 t plus second mode shape into eta 2 t and so on till nth mode shape into eta n t. Now, if I try to write this in matrix form, I can always write it in this form. I can form a matrix R1, R2, so on till Rn, and then multiply with a vector containing eta 1 t, eta 2 t and so on till eta n t. Right. So, you by now know that this matrix is nothing but the modal matrix. So, this matrix is the modal matrix. So, I can write therefore that my degrees of freedom or u1, u2, u2 t till unt is my modal matrix phi into eta 1 t, eta 2 t up to eta n t. Right. So, I can write this whole thing in an abbreviated form as ut is equal to modal matrix phi into eta t. Okay. So, this also I have derived from the modal expansion theorem, which states that my any arbitrary response is equal to my modal matrix into an unknown coordinate eta, which is usually called generalized coordinate or natural coordinate. Right. So, this is what I get. So, I do not know eta. I mean, I would like to reiterate, this is not known to me. I have to solve for this. This is not known yet. So, I need to solve for this. I know this modal matrix is known to me once I know the mass and stiffness matrix, but this eta t is not known and I need to solve it. Now, the next attempt is to see that I have written my ut in terms of my natural coordinate or generalized coordinate. How is this going to be useful? Why did I do this? How am I going to use this? So, let us go back to the equation of motion. So, I have this equation of motion, so which has the M matrix, the mass matrix, which is n cross n, and then I have my stiffness matrix, which is again n cross n, and this is the externally applied force. So, all this while when we were talking about multi-degree of freedom system, our right hand side was 0. We were dealing with free vibration problem. So, now we have brought in the force vibration. So, on the right hand side I have the force vector. So, this force vector is n cross 1 and this are my displacement vector or my degrees of freedom, which is also n cross 1. Now, what I will be doing is that I will write U as my modal matrix phi and eta t. Okay. So, this modal matrix, let us assume that it is mass normalized. Okay. So, I am dropping the superscript m n just to make the expression simpler. So, phi is mass normalized. So, now what I do is I plug this in here. Okay. If I do so, what do I get? I get mass matrix M into phi into eta double dot, then I have my stiffness matrix K, then I have mass normalized modal matrix phi, and then I have eta, and that is equal to F, right. So, what I do is that I again pre-multiply both sides of the equation by the transpose of the modal matrix. So, I multiply both sides by phi transpose m into phi into eta double dot plus phi transpose k into phi into eta is equal to phi transpose into F, right. So, now what happens? So, I have written this equation. So, there is one mathematical advantage. Why? So, this is fine. Here I am just replacing u by phi into eta. But why am I pre-multiplying by phi transpose? Because phi transpose, one advantage is that the orthogonality condition of phi and phi transpose in this form can actually simplify the equation to a great deal. So, let us see what would happen. So, I have this matrix phi transpose m phi into eta double dot plus phi transpose k into phi into eta is equal to phi transpose F. So, now if we remember the orthogonality condition of the mode shapes, we have seen that for a mass normalized mode shapes or mass normalized modal matrix, this product is nothing but an identity matrix. Similarly, this product is a diagonal matrix with the diagonal terms being omega p square, right. So, now if I write down this equation in a simplified form, I will have I into eta double dot, and then I will have a diagonal matrix with the diagonal term as the square of the natural frequencies into eta equal to another vector q t, where q t is nothing but the transform force. Q t is the vector qt is nothing but phi transpose into f, right. F is n cross 1, this is n cross n. So, I have a n cross 1 vector, right. So, now this is going to give us some interesting expression. So, this is a diagonal matrix with the diagonal terms as 1. This is a diagonal matrix with diagonal terms as the square of the natural frequency, and this is a vector. Okay. So, now therefore, this entire set of matrix equation now can be written as a set of ordinary differential equation right, where p is equal to 1 to n, where n is the total number of degrees of freedom. So, what is happening? I initially had a matrix equation which was m u double dot plus k u is equal to f. Of course, these are all vectors and matrices, right. So, this was a coupled equation, a coupled set of ordinary differential equation. So, we solving this set of coupled ordinary differential equation is difficult. To solve them analytically is difficult. Now, what we have done is that by using modal expansion theorem and using this transformation, that my u is phi into eta. By doing this transformation, I have converted this coupled set of ordinary differential equation into a set of uncoupled ordinary differential equation, right. So, I will have a set of uncoupled ordinary differential equation, and if you see this equation, this is analogous to a single degree equation of motion of a single degree of freedom system. So, this is analogous to u double dot t plus omega square u t, and that is equal to some forcing function, let us call it as p t, right. So, I am actually converting a multi-degree of freedom system to a set of single degree of freedom system. So, we all know how to solve this equation for several possible cases, for several possible forms of the applied load. We also know how to solve this equation for free vibration cases. So, since we know how to solve this equation, we also know how to solve this equation for different values of QPT. Therefore, so this whole process is called modal analysis. So, what we do in summary, we convert a coupled multi-degree of freedom system into a set of single degree of freedom system. So, the benefit is that we know how to solve single degree of freedom system. Solution of single degree of freedom system is very easy. So, we can solve this. If we solve this, we are going to get the value of eta p t. Okay. We are going to get the expressions or values for the natural coordinate. Once we get the values of natural coordinate, I can obtain my physical coordinate or the physical degrees of freedom u by using this transformation. So, this concept is a very important concept of structural dynamics or vibration of multi-degree of freedom system, because what we need to know is just the orthogonality conditions of the mode shape. We just need to know the natural frequency, we need to know the mode shape, and we need to know the orthogonality condition of the mode shape. If we know all this, then we can easily convert a multi-degree of freedom system to a set of single degree of freedom system. And the good part is that irrespective of what is m, k and f, the final expression after modal analysis is going to be this, right. Does not matter what is m, what is k, if I do a modal analysis, the final equation is going to be something of this form. Only QPT is going to change for different values of force. Okay. So, let us now next solve an example problem which will help us to clarify what we have learned. So, let us do this problem. So, we have already done part of this problem earlier. So, let us now extend this problem to a force vibration case and try to solve this problem using modal analysis. So, I have this 3 degree of freedom, I have already talked about this earlier. So, only new thing that has happened is that there is an applied force F t acting on the mass m 2, and the force is a rectangular function which has a value of p till t equals to t e, and after that it becomes 0. Okay. So, we need to find out the response of the system due to the applied load at time instant t greater than t e. Okay. So, we have already found out the natural frequencies of the system earlier. We have found out the mass normalized mode shapes of the system earlier. We are not going to redo it, we are just going to use these values and then try to find out the response of the system. So, let us now see how we are going to do that. So, therefore, I have this equation m u double dot plus k into u is equal to the force vector F. The force vector F is nothing but 0 F t and 0. So, there are no forces acting on mass m 1 and m 3, that is in the direction of degrees of freedom u 1 and u 3. The force is acting only on mass m 2, and that is how we write down the force vector. Now, we already know the mass normalized modal vector, modal matrix. Which is phi 1 by root over m into 0.557, 0.557, 0.435 and then 0.707 minus 0. So, it is 0.557 and then I have 0.435, then 0.707. Okay. So, now this is the mass normalized modal matrix. Now, if I do the transformation, so if we do after modal analysis, that is if I write UT as my modal matrix into my eta and then plug this in here, what I am going to get is my eta 1 double dot t plus omega 1 square eta 1 t is equal to q1 t, and then I have eta 2 double dot t plus omega 2 square eta 2 t is equal to q2 t, and eta 3 double dot t equals to omega 3 square eta 3 t is equal to q3 t. So, what is q1, q2, q3? So, as we have said earlier, q1, q2 and q3 t is nothing but phi transpose into the f vector, which is 0, f t and 0. So, let us find out q1, q2, q3. So, what I have to do is take the transpose of this matrix and then find out q1, q2, q3. So, let me take that. So, I have to take the transpose. So, so qt is going to be the transpose of this into 0, f t and 0. This is going to be the transform force vector. Okay. So, if I take this product, if I take the transpose of this multiplied by the force vector, what I get is, I get eta 1 double dot t plus omega 1 square eta 1 t is going to be 0.557 by root over m into f t. Okay. And then eta 2 double dot t plus omega 2 square eta 2 t is going to be minus 0.707 root over m into f t, and then eta 3 double dot t plus omega 3 square eta 3 t is 0.435 by root over m into f t. So, we know that f t is a function like this. So, this is p, this is t is equal to t e. So, this is the function like this. So, now this is very similar to the single degree of freedom system. So, I can use convolution integral or Duhamel integral. Using convolution or Duhamel's integral, I can straight away write that eta 1 t So, for I want to obtain the response when t is greater than t. So, I can write eta 1 t is nothing but 0.557 by root over m into the integral from 0 to t f t into h t minus tau is f tau into d tau. So, I have to, since the force is discontinuous, I have to write this as m 0 to t e, this is going to be p h t minus tau d tau plus t e to t, where f tau is nothing but 0 into h t minus tau d tau into this. So, this goes to 0 because this is 0. So, I have 0.557 by root over m into p into integral of 0 to t e h t minus tau for an undamped case is going to be sin omega 1 t minus tau by omega 1 into d tau, right. So, we have done this exactly similar thing for a single degree of freedom problem. So, we are now just extending it to the multi degree of freedom system, right. So, I have got eta 1 t as 0.557 p by root over m into omega 1 into 0 to t e sin omega 1 t minus tau d tau. So, if I evaluate this integral, I am going to get 0.557 p by root over m omega 1 square into cos omega 1 t minus tau with the limit from 0 to t e. That can be written as 0.557 p by root over m omega 1 square, and then I will have cos omega 1 t minus t e minus cos omega 1 t. So, this is going to be the solution of eta 1. So, it is very straightforward. So, say that eta 2 similarly would become minus 0.707 p by root over m omega 2 square into cos omega 2 t minus t e minus cos omega 2 t. And similarly, eta 3 t is going to be 0.435 p by root over m omega 3 square into cos omega 3 t minus t e minus cos omega 3 t. So, these are the solution for the generalized coordinate. So, the actual physical coordinate u1 t, u2 t and u3 t is going to be just 1 by root over m into the entire modal matrix phi, I mean the mass normalized modal matrix, I know the values of those, into my eta 1 t into eta 2 t into eta 3 t. So, this is going to be 0.557, 0.557 and 0.435, 0.707 minus 0.707, 0.435, 0.435 435 minus 0.557. So, we know the expression for eta 1, eta 2, eta 3. I can always multiply by this, and then that will give me the actual response U1, U2, U3. So, this is for a particular case. So, given any force F t, we can use this method and analytically find out the solution of U1, U2 and U3. So, this is called the modal solution by modal analysis. Thank you.